All right, let's keep moving on through the dot product. So as mentioned at the beginning of the section, the dot product is a powerful tool as well to find the angle between two vectors. Okay, well we got this definition at the beginning on the previous page. So if we rearrange this equation for the trigonometric function, we'll solve for cosine first and then solve for theta. That's going to give us the angle between the two vectors. And well, what do we need in this case to find the angle between the vectors? The dot product in the numerator and the magnitudes in the product of the magnitudes in the denominator. All right. Well, of course, there are some important properties, or keywords, if you will. In this case, whenever we have two vectors having a 90 degree between them, that happens when the dot product is 0, and we say that these vectors are normal or orthogonal or also perpendicular, of course. But I mean, again, the term perpendicular is mostly used in 2 dimension, 3 dimension, but beyond through the 3rd dimension, we use a more abstract terminology, in this case the orthogonal, but it's also used for 2D and 3D as well. All right. Now, when two vectors are parallel, it is the case that either the angle between the two vectors is 0 degrees, that is, we have the two vectors like this in the same direction, or 180 degrees, facing in the opposite direction, but still having, sort of the same angle. So that's really, 180 degrees versus no angle in between, or 0 degrees between the two angles. And well, let's find the angle to the nearest 100 of a degree between each pair of vectors. Well, so what do we need in this case? Find the dot product between the two vectors, and then in this case we have two vectors in 2 dimensions. And the following example is one with in 3 dimensions. So let's find the dot product. U dotted with V. That is, how about we write this in component form: 5, -3, and 2, 1. Okay? So the dot product, which is 5, -3, dotted with 2, 1. And this is 5 times 2, which is 10, minus 3, which is 7. We also need the magnitudes of the two vectors here in this case. The magnitude of U, which is the square root of the sum of the squares of the components, and that's 5 squared, that's 25, plus 9, is that 34? Square root of 34. And the magnitude of the vector V, that's the square root of 2 squared plus 1 squared, and that's 2 squared is 4 plus 1, that's 5. Square root of 5. So we got all the information we need to find the angle between the vectors. Okay, so coming back to the formula from, let me take it from here. Cosine theta, let me scroll this down, equals U dotted with V divided by the product of the magnitudes. So let's put numbers to this. Well, the dot product is 7. The magnitude of U, which is the square root of 34, times the square root of 5, and theta will be arc cosine, or cosine inverse, either notation is fine. 7 over the square root of 34, and this should be approximately 57 53 degrees. And again, be careful that your calculator is set in degree mode. All right. Let's have a look at letter B. So, number one of the two pieces of information to find the angle between the vectors is the dot product which lies in the numerator. Alright, so that's u dotted with v. In this case, 1, 5, negative 3. So that's 1 times negative 2, so that's negative 2, 5 times 4, that's 20, 6 times 3, that's 6 times negative 3, that's negative 18, and this adds up to 0. Well, whenever the dot product of the vectors is 0, what does that mean from the definition at the top?
90 degrees.
There's a 90-degree angle, right? So that means that the two vectors are orthogonal. Well, that means they look like this, and that's 90-degree angle between them, right? So, and in this case, you don't need to keep going and compute the formula, because even if you did, I mean, cosine theta equals 0 over whatever their magnitudes are. I mean, it's 0 over a number, that's 0, and yeah, you know. So the angle in this case, oh, they're asking for the angle theta, which is 90 degrees. All right. All right. The next topic in this section is projections and vector components. All right. So, well, what we did in sections 13.1 and 13.2 was, well, describe what vectors are, but on top of that we did addition of vectors and to get a resultant vector, you know, obtaining new vectors and applications of physics of total forces, velocities, etc. But in some cases we may be in the need of doing the reverse process, which is in this case given a vector, decompose it into its components x and y for an now, right? So, and in this case, well, we decompose these two vectors into orthogonal components, and well, we're going to use this new term called projections. And well, so we have two vectors u and v, for which u is going to be defined. So yeah, just bear with me with a lot of symbols here. Everything has its own meaning. You'll see how this will work out in the end. Okay, so this vector u, it's going to be decomposed between w1 and w2, right? Where w1 is parallel to the vector v and w2 is orthogonal to vector v. Okay, so let's look at a diagram so you can see a picture, and I think it's better if we, okay, so we have vector u and vector v, all right? And this vector u will have these two components w1, and which is, I'm going to draw, okay, w1 which is parallel to v, that is, it goes in the same direction, but it doesn't go on forever. It just goes as far as the point where I can draw the second vector pointing to the head of the first vector. All right? And let's label this respectively w1 and w2. And w2, as mentioned before, that is orthogonal to the vector in the direction of v. That it forms a 90 degree here. All right? So this vector w1 is the projection of the vector u onto the vector v. Well, I mean, in more simpler words, think of vector W1 as the shadow casted by the vector U. For example, if we have the sun here, right? This vector W1 is the shadow of the vector U projected onto the vector V. That's what the projection is ultimately, okay? And well, so the other vector W2, which is U minus W1, well, where am I getting that equation? Because think of U, the vector U, as being the resultant vector between W1 and W2, adding those two vectors like actually using the triangle method like last time, right? So that's where this sum is coming from, just so it doesn't look like too mysterious. Okay, so let's write that down. Let's see. Okay, well, no need to rewrite them. Okay, so from this situation, from this diagram, we can derive a formula for the projection of that vector U onto the vector V. Well, so let's start using having some symbols here, and this U to be the projection of the vector U onto the vector V. That's how we read this notation. Well, this quantity right here, which looks like I just got it like out of nowhere, but well, it has a meaning. Okay, without the K, V over, well, it's not absolute value, it's actually, I think I need another bar here, double bar. It's the vector divided by its magnitude. What's that? 1. It's 1. It's a unit vector, right? But if we multiply a unit vector by some value K, well, it's a new vector. So that vector is W1. It's a unit vector times some constant. And well, for the sake of simplicity of the derivation, let's consider K as a positive value. All right, so let's see. From this diagram right here, we can use our trigonometry. In particular, cosine theta, which in this case is adjacent over hypotenuse. And well, the adjacent side will be the magnitude of this vector W1 over the hypotenuse, which is the magnitude of the vector U. Okay, so that's one piece of information that we get from the diagram. Yes?
Where is theta?
Theta should be this one right here.
Wouldn't that be W2 over W1? Or wait,
yeah, cosine, which is adjacent over hypotenuse. Yeah, thank you. I forgot the theta usually is the acute angle. But we also have another piece of information from the definition of the dot product, or rather the angle between the vectors. So we can connect this with cosine theta equals the dot product of U and V over their magnitudes, the products of their magnitudes. All right. Well, cosine theta equals this madness, and cosine theta equals also this madness. How about we put together the two madnesses, okay? So the magnitude of W1 over equals the dot product well, let's solve for the magnitude of W1, because well, that's our target in this case, because that's what we want to find with it is. Well, in this case, how about we multiply both sides by the magnitude of U. But see what's going to happen here? It will get canceled on both sides actually. And well, so in this case, we're going to be left with magnitude of W1 equals the dot product all right. Okay, but let's think of this. What is this expression that we obtain here? Does the result of this calculation is that going to give us a new vector or just a number? That's scalar, right? Because it's a magnitude. So this quantity right here is k. And we call this, we have a special symbol for this, scale of the vector u onto v. Well, that is the magnitude of the vector v, or the length of that vector. In other words, to keep this simple, it's the length of this shadow. That's all it is. All right? So now I'm going to go back to the projection formula. All right, so for the projection formula, in this case, I'm going to put together this. So projection, starting from here, u onto v, it's W1. All right, but W1 was described this way, k times v over its magnitude. But what do we have for v? We have this, isn't it? So this will be, okay, let me highlight it just so you can see what am I doing here. So this expression is going to go here. And what do we have? U v over v, rather magnitude of v, times the vector v over its magnitude. And while simplifying this a little bit, this is going to be the dot product in the numerator over the magnitude squared times the vector, which is this formula here. All right? Okay, so let's look at one example. So we have a couple of vectors in 3 dimensions. Okay, do you still? So we have 2 vectors in 3 dimensions. The vector 3, 5, negative 2, and the vector v, 0, 2, and 4. And they're asking us to find actually both projections. The projection of u onto v and the projection of v onto u. And they're also asking us to find the scalar projection of v onto u, which in this case is the magnitude of, or the size of the shadow of v onto u, basically. Okay, so what do we need in order to find projections? Of course, we need magnitudes and we need dot product. So how about we do that first? So let me do the dot product here at the top. So u times v, and well, so 3 times 0 plus 5 times 2, and negative plus negative 2 times 4. So that's going to give us a 0 plus 10 minus 8, which is 2. Is that the dot product? 2? Mm-hmm. And let's also find the magnitudes of the vectors, the magnitude of u. So that's the square root of 3 squared plus 5 squared plus negative 2 squared. And then, so that's going to be the square root of 3 squared, which is 9, plus 25. 25 plus 9, is that 34? Plus 4, is that 38? Square root of 38. And the magnitude of v, in the same way, just the square of its magnitude, 0 squared plus 2 squared plus 4 squared. Okay, that's the square root of 4 plus 16, is that 20? I know we can simplify 20 as 4 times 5 and then 2 root of 5, but let's just leave it like this for now. Okay? So let's find projections. Oh, I don't want to hide this. We need this actually. Let's highlight maybe the numbers that we need. So the projection of the vector u onto the vector v. So the vector that's actually the shadow, that's the one that is written as a subscript of the word prog. All right? And well, in this case, the formula u v over the magnitude of v squared times or v. And well, what do we have for the dot product? The dot product, which is 2 over the product of the magnitudes, which is the square root of 38 times the square root of 20. That times the vector v, which in this case, careful, it's 0, 2, 4. All right. So let's simplify this number. That's going to be, oh yes, it's squared. My bad. Yep. Just realize that. So that's the square root of 20. Quantity squared. Yes, I think I was thinking of the angle between the vectors. So that's 0, 2, and 4. Okay. The square cancels the radical. That's going to leave us with a 2 over 20, which reduces to 1/10. Which multiplies to get, well, still 0. And 2 over 10, that's a fifth. And 4 over 10, is that a 2 over 5?
Mm-hmm.
All right. So that's the vector that becomes the shadow when u it's on top of v. And well, of course, I think no, they're not asking us for the scalar yet, not yet. So let's do the projection the other way around. So that's number 1. That's number 2. That's the projection of, in this case, v onto u, not u, onto v. And well, all it's going to change in the formula, I mean, the dot product remains there. What changes is this v right here. It's going to become u this time, all right? Because it's the projection the other way around. I mean, even if you reverse the order of this, I mean, it's commutative property of numbers, I mean, of vectors more particular. So let's write it down as a formula. That's u dotted with v over the magnitude squared of u, and that times the vector u. Let me just highlight that part. I think it would be great. So when the shadow, and just so you can see what we change when we, in the case that we change letters, because we will when we turn this into forces to see the projections of forces, we're going to use different letters. Okay, so well, we have the dot product, which again is 2 over the magnitude of u squared, which in this case is 38 squared, square root of 38 squared, times the vector u, which is 3, 5, negative 2. And well, so again, the radical cancels the square, and that becomes a 2 over 38, which reduces to 1 over 19. 1 over 19, 3, 5, negative 2. All right. And this is 3 over 19, 5 over 19, and negative 2 over 19. Well, in this case, I'm using component form, but I mean, you could be asked to write these vectors in the IJK notation. Just erase the commas and the angular parentheses, and change IJs and K in the corresponding signs again. Well, the third part of the problem, find the scalar, the magnitude of that projection. Well, we don't need to find that the magnitude of this vector using the formula, because if we rewrite this formula again, this is the same as saying this formula came from doing u and v over the magnitude of u times u over the magnitude of u. But remember, this part right here was that scalar from, let me scroll, let me go back to the derivation part. That scalar right here. And we can just compute that without squaring the magnitude of u. So the scalar projection of v onto u will be u dotted with v over the magnitude of u. And in this case, well, it's also 2 over the square root of 38. Final answer. So that's the size of the shadow. That's what we're finding in here. All right, applications of the dot product. So let's see. Applications to work and force. Well, this is something we cover as well in Calculus 2, finding work using integration. But in this case, we're going to do it using vectors again. In general, work equals force times the distance. Okay. This very simple formula only works, however, when the direction of the force is the same direction as the motion of the object. For example, if I push the chair here, in this case I'm pushing it with an angle. My arms are producing an angle, so that formula it's no longer going to work for the situation unless I'm at the exact level in the horizontal direction as in this case the floor, right? And that describes the motion of the chair. So for this reason, well, we have to multiply that by the cosine of the angle. And well, I mean, does that formula look familiar from the beginning of the section? Isn't it the definition of the dot product? Mm-hmm. Knowing in this case the magnitudes of the forces and the angle. So that's how. Well, as a little diagram here again. So we have some force in this direction, in a diagonal direction, in a not perfectly horizontal, and we're moving this a distance d. All right, with an angle theta. So force times distance, work equals force times distance. But in this case, well, not yet. And in this case, well, we're going to introduce that shadow vector, which is the projection of the force, because ultimately, when I push the chair, for example, here, yes, I'm applying a force of whatever newtons, but it's not evenly horizontally, so ultimately, it's an inclined force projected on the horizontal vector, which is the distance displayed in which I displace the chair. So in this case, that's how we relate this calculation of work in terms of projections using the formula we've been using for the last few minutes. So in this case, this W1, all right, will be the projection of the force onto not the vector v, onto the distance vector, onto the displacement medium. Okay? And well, using the same formula, but now using the new letters, this will be the dot product of the force times the distance divided by the magnitude of the distance vector or displacement vector squared times the displacement vector. Okay? So that's putting, this projection situation in a physical context. Well, from here, what can we do? Well, let's do one example. So we have a toy wagon that it's pulled by exerting a force of 25 pounds on a handle that makes a 20-degree angle with the horizontal axis. Okay? And find the work done in pulling the wagon 50 feet. Okay. A diagram as usual. We have a force and there's an angle of 20 degrees with a distance vector along some distance. Okay? So, well, in this case, we are not going to compute any dot product or any magnitude of the vector, because in this case, the magnitudes are given, so all we do is just multiply three numbers here. That's it. Okay, let's write that information that we have. So in this case, we have the magnitude of the force, which is, in this case, 25 pounds. And the magnitude of the distance in this case is how far are we going to displace the toy wagon, in this case 50 feet. And this is, the 50 feet. And well, we want to know the work. In general, work equals force times distance, but now we introduce these arrows because we're working with vector notation. Yes?
Why can we use two different units between force and distance?
Force and distance. Oh, one is, this is pounds, in this case, of force, and then the feet. So when we multiply the two together, is going to be the feet.
Like in the diagram there.
Do you mean, okay, do you mean in this case, okay, let me, pounds and feet? Yeah, pounds and feet. So it's the force we apply along certain distance, so that's the work. So in this case, well, in terms of the magnitudes, cosine of 20 degrees, and again, just make sure that we have, cosine theta first, and that's 25 pounds times 50 feet, cosine 20 degrees. And this is going to be approximately 1174.6 feet pound. All right. Oh yes, yeah, we have a couple, one more page, right? Okay, another situation in which we use projection to find parallel forces and normal forces. Okay, so in the form of a diagram, let's get a diagram here. This is a vector v. And in this case, for example, when we park a car or a motorcycle on an inclined street, all right? So there is a minimum force that is required to keep the car from sliding, So, and that's due to gravity. So let's put this force in pointing down. All right? But this force right here, guess what? This is the force that we will decompose into its two components. One that is this, the orthogonal. It's orthogonal to vector v, and the one that is parallel to vector v. This is our W1 and W2. In this case, well, it looks weird because of the orientation of the picture this time, and we are not focusing. We're not decomposing the vector v. In this case, we're decomposing the vector f, the force in this case. And well, so in this case, this vector W1 is the projection of the force onto the incline. Right? It's like having, it's kind of weird to have the sun in the sun below, maybe like a lamp illuminating and casting the force vector, casting the shadow onto the incline. So yes, and it's kind of weird having like an inverted shadow, right? But if we were interpreting it the same way, that's pretty much the picture. So let's see. So they're asking us to find the components of the vertical force F 0, -5. Well, so notice the signs of the components of the vectors are consistent with the situation, in this case going down for the vector, in the directions parallel to and normal to the plane that makes an angle of pi/6 with the positive x-axis. So, yes?
Is W1 and W2 make a right triangle?
Yes. So in this case, when we add W1 plus W2 using the triangle method, we get F, the resultant vector. But well, that's what we did in the previous section. But in this case, what we do is the reverse: having a vector, decomposing it into the two vectors W1 and W2. So let's see what we have. Again, a diagram always helps. So we have the vector v, okay, and we have some force. Let's call it F, the force F. And of course, again, this force is decomposed into W2, which is orthogonal to the vector v, and W1, which is parallel or in the same direction as the vector v. And let's label our information. So in this case, we have the vector f 0, -5. Okay. So, of course, we need another vector. It seems like we're missing some information, and well, it's a little cryptic the way we're gonna get the second vector, because all we know is the angle. So we need to go back to a definition we covered in section, I believe it's 13.1 the last time. We can define vectors if we know their angles only. So let me recall that. So a vector v, it can be a unit vector, cosine theta and sine theta. However, if we also know the magnitude of the vector, so in this case, well, to make this a lot simpler, let's use the unit vector version to obtain the second vector. In this case, okay, v cosine, we know the angle is pi/6, sine pi/6. And cosine pi/6 is √3/2 and 1/2. So that's going to be our vector, yes?
Wait a angle between, wait, there's the vector v, how do you know it's pointing up and right and not down and left? Or can you choose it?
Well, to keep it simple, we put it in like, we orient it to the, well, if we had like the Cartesian plane here to the first quadrant, because, well, ultimately it's still relative to the ground. Even if I had this arrow pointing the other way around, it's still, in this case, 60 degrees or 30 degrees or pi over 6.
So we could solve the problem if the vector was pointing down left as well?
Yes.
Okay.
But in that situation, well, yes, it would be a force pushing up in this case, all right? Because in this case we have this force, in a way, due to gravity. So that's why we're having this in the pointing up, and preferably in the first quadrant.
Wait, so shouldn't the angle in this case be 120 degrees instead of 30?
Well, let me see. So if we have like our Cartesian here, Cartesian plane, it would be this angle, right? It's still pi over 6. If we set it on the first quadrant.
So the angle that you use to find the v vector, I thought, okay.
Yeah.
Never mind. So the other 120 would be the angle for the projection once you actually solve it.
Yes, exactly. Yeah, that'll be kind of, the orientation. Even if we do this, it's even in the third quadrant would be something. Yeah, that's right. And well, so we got the two vectors, and let's find. Well, for the projection, of course, there's two pieces of information that we need: the dot product and the magnitude of the vector. But I mean, well, a lot of the work right here is going to get simplified because we have a unit vector here. And what's the magnitude of that unit vector? 1. So we wouldn't need to find that. So the projection, well, first of all, f dotted with v, that's root of 3 over 2, 1/2 times 0 comma -5. Well, the first component is 0 still, and -5 halves. All right. So, oh, wait a minute. No, that's not a new vector. That's simply -5 halves. It's a scalar, right? So let's see. No, the vector, we do it later. So the projection of the force onto the vector v will be the dot product of the two vectors over the magnitude of, in this case, v, which is where we are projecting our force, times the vector v. Well, the dot product we already calculated before. Isn't that -5 halves? And, oh, this is squared. And, well, what's the magnitude of v again? 1 times vector v, which is this unit vector, root of 3 over 2 times 1/2. All right? I know, I could have just say, oh, -5 halves times that unit vector, but I mean, it's important to write where are we getting this vector v and how are we setting this dot product. So that's a -5 halves, root of 3 over 2, and 1/2. So that's going to be -5 root of 3 over 4, comma, -5 over 4. Okay? Okay, now coming back to your question, Anna, so the position of that vector projection, and just to check the consistency of the calculations with the consistency of the picture, so let's check the signs of the components. So we have negative for both, and if we look at the direction of this vector, isn't it like the third quadrant, negative and negative? So for sure it's going to lie on an angle that that is going to be on the third quadrant. All right?
I think I just skipped this stuff because I was solving the product of F and P, and I was using the two magnitudes and.
Oh, the two I think yeah, the same mistake I did before, right? I see. See what you did.
Question.
Yes.
So I understand where we got the v vector, it's cosine pi over 6 and sine pi over 6, but why is that a unit vector?
Yes. Okay. Let me go back to section. So yes, we have the slope right here, and we have the slope where the motorcycle is parked on. The force acting in this case, well, due to gravity, and well, not due to gravity in this case. We are using the force in this case in terms of the weight of the motorcycle. And well, these are the two components of the vectors. But let's define this vector. This vector f. How do we define this vector f in component form? Any ideas? What would be the x component, the x component of the vector? 0. What about the y component? 200. How about negative 200, because since it's weight, it's going down. So yes.
Wouldn't we also add gravity, the mass and the gravity?
Oh.
Down.
Yes, I mean that's true, but in this case I guess we're already including in the because pounds it's due to weight in this case. I suppose that if we were using the metric system in which we use grams, which is just the amount of mass, that's a good question. But pounds in that already include the gravity thing. Okay. So let's see what's next. Okay, so the unit vector v. Cosine 10, sine 10, whatever that is. So for now, let's leave it like this. We do the calculation later. And well, we want to know the force. The only one force that we need to calculate is W1, because that's the force the minimum force that we need to, so the motorcycle doesn't roll down the hill. So in this case, well, W1, which is the projection of the force onto V. And that requires to find the dot product and in this case, the magnitude of V, which in this case the slope where it's parked on. But in this case, for the sake of simplicity, we're using that unit vector. So in this case, f dotted with V, that's 0, negative 200 times cosine 10 sine 10. And well, in this case, so 0 and negative 200 sine 10. Well, actually, again, negative 200. I did the same mistake before of writing another vector, but it's just a number. So negative 200 sine of 10 degrees. Let's leave it like this for now. This is going to go here. And again, what's the magnitude of this vector, cosine 10 sine 10? 1, because it's a unit vector, right? So this means the dot product, which is negative 200 sine of 10 degrees over 1 squared, all right? That times the vector V, which in this case is cosine 10 sine 10. Okay? And well, 200, negative 200 sine 10, this is according to my notes, it's negative 34.73 approximately. cosine 10, sine 10. Well, again, keep in mind that this type of questions could lead to certain ambiguity because they're asking us to find the force. But again, it's not clear whether this force as a vector or as an actual number. That's why we need to compute both. Well, number one, find the vector, and also, okay, let me keep simplifying this. That's negative 34.202, comma, negative 6.03. So in this case, we want to find the magnitude of this vector to actually find that force, that minimum force. So that's the magnitude of W1, that's the square root, negative 34.202 squared plus negative 6.03 quantity squared. Okay? And that magnitude, according to my calculations, check on your calculator, should be 34.7 pounds. Is it?
Yes.
It is? And I think this is the last exercise, and this is the end of the section. Well, I was hoping to get into cross product today. Well, let me just briefly show you what we're going to do next time. So, for cross product, we need a little bit of matrices in finding determinants. And you may have done this in in pre-calculus or in intermediate algebra when you solve systems of equations using the Cramer's rule. Or those of you actually that may have taken linear algebra already, or you are currently taking, well, that's chapter 3 in linear algebra. So you may already have some information on computing determinants of matrices, but we're going to do that next time. So